morning, dear students. Today we are going to look at linear programming module lecture number 6. The title of today's lecture is the Big M Method. Continuing our discussion on how to solve a general linear programming problem, last time we studied the simplex method. Today we will be talking about the Big M method. This is a sister method of the simplex method and is applied to linear programming problems which have a slightly different kind of a situation. So, let us see how this method works. The outline of this talk is as follows. We will be studying at LPP with greater than or equal to constraints. Then we will talk about the Big M method. Then we will look at an example and finally some exercises. Let us look at this linear programming problem. The problem says we want to minimize a function of 3 variables as follows: minus 3x1 plus x2 plus x3, which is subject to 3 constraints, where the first constraint is of the less than equal to type, the second constraint is of the greater than or equal to type, and the third constraint is of the equality type. The first constraint is x1 minus 2x2 plus x3 less than or equal to 11. The second constraint is minus 4x1 plus x2 plus 2x3 greater than or equal to 3, and the third constraint is twice x1 minus x3 is equal to minus 1. All the xi's, that is x1, x2 and x3 should be greater than or equal to 0. Now, what is the way in which we apply the simplex method that we learnt last lecture? Yes, we need to convert the given LPP into the LPP in the standard form. What does this mean? It means that the objective function should be converted to the maximization type. All the inequalities should be converted into equality constraints, and thirdly, all the right hand quantities of the constraints should be greater than or equal to 0. So, let us convert the objective function into the maximization type, and for this we will multiply the entire objective function with the negative sign. As a result, we get 3x1 minus x2 minus x3. So, this is the objective function for the LPP in the standard form. Now, the first constraint was of the less than equal to type, and therefore, in order to convert this inequality into an equality, we need to add a variable which we will call as x4. And what is this x4? This x4 is called as the slack variable. So, the original inequality x1 minus 2x2 plus x3 less than equal to 11 will become x1 minus 2x2 plus x3 plus x4 is equal to 11. And as you know, x4 should be greater than or equal to 0. Coming to the second constraint. The second constraint minus 4x1 plus x2 plus 2x3 greater than or equal to 3 will need to be converted into an equality constraint by subtracting a positive variable, and that positive variable is called as the surplus variable. So, therefore, we lead to an equation minus 4x1 plus x2 plus 2x3 minus x5 is equal to 3. Please note, x5 should be greater than or equal to 0. Now, you might ask, why do not we write x4 in both the equations? No, we cannot write x4 in both the equations because the inequalities are different. Both the inequalities, the first inequality and the second inequality, are totally different inequalities, and therefore, we need to use different variables, and that is what we do. In the first inequality, we add a slack variable which is called as x4 in our case, and similarly in the second inequality, we subtract a positive variable which is called as the surplus variable. So, minus x4 has to be subtracted from the equation. Now, coming to the third equation, in the given problem we have got twice x1 minus x3 is equal to minus 1. Although it is an equality, it is fine, but the trouble is that the right hand side is not positive. So, therefore, we need to convert the third equation in a form where the right hand side is positive, and therefore, we will convert this equation like this: minus 2x1 plus x3 is equal to 1, and x1, x2, x3 were already greater than or equal to 0. On the other hand, the two new variables that we have introduced, x4 and x5, they also have to be greater than or equal to 0. So, therefore, we have converted our given LPP into the LPP in the standard form. So, we have a question before us: how to start the simplex procedure, because we do not have a initial BFS, and the answer to this question lies by introducing artificial variables in those equations which do not have a basic variable, and we will introduce one artificial variable in the second equation. Let us call it x6. Similarly, we will introduce another artificial variable in the third equation. We will call it x7. So, the artificial variables x6 and x7 will be added to the second and the third equations. However, we have to make sure that these variables should be greater than or equal to 0, and when we apply the simplex method at some iteration or the other, these artificial variables should be reduced to 0. And how can they be reduced to 0? They can be reduced to 0 by throwing them away from the basis, and that is what we are going to do. So, therefore, our given problem becomes the following: maximize 3x1 minus x2 minus x3 minus m times x6 minus m times x7, where m is a very large number going to infinity. What is the reason behind introducing these two terms in the objective function? Because, as I said, these artificial variables x6 and x7 are in the beginning of the simplex calculations, they are non-zero, that is they are in the basis, because what is the BFS in this system of equations? The initial BFS is x4 is equal to 11, x6 is equal to 3 and x7 is equal to 1, all others 0. But we do not want x6 and x7. Therefore, in order to reduce them to 0, we will need to make some modifications in the objective function. And what are those modifications? We will multiply these artificial variables with a very large quantity with a negative sign, and since we are going to maximize the objective function, therefore, they will be pulled to 0. That is the reason why we need to add two terms minus mx6 and minus mx7 into the objective function. Now, you will observe the first equation is as it is, x1 minus 2x2 plus x3 plus x4 is equal to 11. The second equation minus 4x1 plus x2 plus 2x3 minus x5 plus x6 is equal to 3. Here, as you remember, x5 is the surplus variable, whereas x6 is the artificial variable, which was originally not present in the problem, but we had to introduce x6 because we did not have a initial basic variable in the second equation. Similarly, in the third equation, it becomes minus 2x1 plus x3 plus x7 is equal to 1. Again, x7 is a artificial variable because it was not present earlier and we did not have a initial basic variable in the third equation. Of course, all the variables xi's from I equal to 1, 2, 3, 4, 5, 6 and 7 should be greater than or equal to 0. And once we get this model, now a readily available BFS is there. And what is that BFS? x4 is equal to 11, x6 is equal to 3 and x7 is equal to 1. This is a canonical system and we have got a initial BFS to start the simplex procedure. Of course, we have to incorporate these modifications into the objective function to take care of these artificial variables, so that at some iteration of the simplex method they are reduced to 0. So, let us now write down the initial table of the simplex procedure. As you can remember, the second column is the basis column. So, we have x4, x6 and x7 as the basis, and we write down x1, x2, x3, x4, x5, x6 and x7. Under these columns, we write down the coefficients that are given in the problem. So, I want everybody to write down these values. Here you find the coefficient of x1 are 1, minus 4, 2, 1, minus 4, minus 2. Similarly, the coefficients of x2 are minus 2, 1 and 0, minus 2, 1 and 0. Similarly, under x3 we have 1, 2 and 1. So, under x3 write 1, 2 and 1. Now, x4 is the basis. So, therefore, x4 is the basis. So, therefore, its coefficients are 1, 0 and 0. Similarly, the coefficients of x 5 are 0, minus 1, 0. So, under x 5 we write 0, minus 1, 0. Again x 6 is the basic variable. So, therefore, it will have coefficients 0, 1, 0. Here x 6 is 0, 1, 0, and similarly x 7 is 0, 0, 1, x 7 is 0, 0, 1. In the last column we will write the right hand side of the problem, that is 11, 3 and 1. On the first column we need to write the coefficients of the basic variables in the objective function. So, what are the coefficients of objective function? The coefficients of the objective function are 3, minus 1, minus 1. So, this will be written on the topmost line. So, here they are 3, minus 1, minus 1. X 4 and x 5 do not appear in the objective function. So, therefore, their coefficients are 0. However, x 6 and x 7 they appear in the objective function with a coefficient minus m. Therefore, the coefficient of x 6 and x 7 are minus m in each case. In the first column we need to repeat these values of the coefficients of the basic variables which appear in the objective function. So, the coefficient of x 4 is 0, the coefficient of x 6 is minus m, coefficient of x 7 is minus m. Next, we need to look at how we should apply the next iteration, and as you remember we need to calculate the deviation rows. So, how are the deviation rows calculated? They are calculated for each variable by subtracting the product of the z0 vector with the column x1 vector and subtracted from the coefficient of x1 in the objective function. Therefore, what will be the first one? The first one will be 3 minus 0 minus m multiplied by 1 minus 4 minus 2. Now, if you multiply 0 minus m with 1 minus 4 minus 2 and subtract it from 3, you will get 3 minus 6m. Please check, you should get 3 minus 6m. Similarly, so this 3 minus 6m we will write over here in the first entry below the x1 column. So, 3 minus 6m. Next, we will again calculate the second entry, and what is the second entry? Minus 1 minus 0 minus m multiplied by minus 2 1 0, and the answer that you get is m minus 1, and this m minus 1 will come at the place in the deviation rows under the x2 variable column. Similarly, for the x3 we have minus 1 minus 0 minus m multiplied by 1 2 1, and that gives us 3m minus 1. So, this value comes under the x3 column, 3m minus 1. The fourth entry is 0 minus m multiplied by 1 0 0, which comes out to be 0, and this is written over here under the x4 column. Next, the x5 entry. This is 0 minus 0 minus m, 0 minus 1 0, which comes out to be minus m, and therefore it comes out to be minus m, and it will be written under x5. Similarly, for x6 and x7 we have the entries as 0. Therefore, our deviation row is completed, and what is the criteria for deciding which variable should enter into the basis? We did it in the last lecture. Yes, the criteria is to look at each of these entries in the deviation row and determine the largest of them. What do we find? We find that 3m minus 1 is the largest entry in the deviations row. So, therefore, this indicates that 3m minus 1, the variable corresponding to 3m minus 1, that is x3, should be the entering variable. So, here is our decision: x3 should be the entering variable in the basis. Now, we have decided x3 should leave the basis, should enter the basis. Now, we want to see which variable should leave the basis, and what is the method for determining that? Yes, the method is to find out the minimum ratios. So, the minimum ratios are calculated as follows. Now, the pivot column is 1 to 1. Why 1 to 1? Because it is under the x3 column. Look at this, under the x3 column, this is the pivot column, 1 to 1, under x3 column is the pivot column. So, we need to perform the minimum ratios between the right hand side and the pivot column. And what are the minimum ratios? The minimum ratios are 11 upon 1, 3 upon 2 and 1 upon 1. And which one of them is the minimum? 1, that is the last entry. Therefore, what does this indicate? This indicates that x7 is the variable which should leave the basis. X7 is the variable which should leave the basis, because the minimum ratio corresponding to x7 is indicating that it should leave the basis. Therefore, this indicates that the entry which is highlighted in the pink cell, that is 1, that is the pivot. So, 1 is the pivot, indicating that x3 should enter the basis, x7 should leave the basis. And in order to perform iteration, we need to apply the elementary row operations in such a way that this pivot column now becomes 0, 0 and 1. So, what are the pivot operations that we need to perform? The elementary row operations to be performed should be R1 has to be replaced by R1 minus R3, that is this operation has to be applied into the entire R1, all the entries of R1. Similarly, R2 has to be replaced by R2 minus 2R3, and what will happen? This will make the pivot column as 0, 0 and 1 under the x3 variable. So, the column corresponding to the x3 variable becomes 0, 0 and 1, and that is what we wanted, because x3 has now entered the basis and the resulting table looks like this. So, here you can see under the x3 column we have entries 0, 0 and 1. So, that completes our first iteration. Again we need to repeat this procedure, and since we now have the new basis according to the criteria, the corresponding entries of the coefficients of the objective function will be introduced into the basis, and similarly the left hand side, the first column will become 0, minus m and minus 1. Why is minus m? Because here we have in the coefficients of the objective function 0, minus m and minus 1. You must make this change in the C0 column, otherwise the calculations will become wrong. Therefore, now we need to repeat the process, obtain the deviation rows as before. So, the deviation rows become as follows: 3 minus 0 minus m minus 1 multiplied by 3 0 minus 2, which comes out to be 1. Similarly, the second entry minus 1 minus 0 minus m minus 1 multiplied by minus 2 1 0, which comes out to be m minus 1, and the third entry is minus 1 minus 0 minus m minus 1 0 0 1, which comes out to be 0. Next one is 0 minus 0 minus m minus 1 multiplied by 1 0 0, which again comes to be 0. Next one is 0 minus 0 minus m minus 1 multiplied by 0 minus 1 0, which comes out to be minus m. Minus m minus 0 minus m minus 1 multiplied by 0 1 0, which comes out to be 0, and the last one is minus m minus 0 minus m minus 1 multiplied by minus 1 minus 2 1, which comes out to be 1 minus 3m. All these entries will be recorded in the last row of the table number 2, and you can see 1 m minus 1 0 0 minus m 0 1 minus 3m. These are all the entries which we have obtained after calculating the deviations. And as before, what is the criteria for deciding which variable should enter the basis? Yes, we need to look at the largest of these entries. And which one is the largest? The largest is m minus 1. It corresponds to the variable x2. Therefore, our decision becomes that x2 should enter into the basis. So, x2 is the entering variable in the basis. Therefore, this is the pivot column x2, the column under x2 is the pivot column. Next, we need to decide which variable should leave the basis. For this, we need to perform the minimum ratio test between the right hand side and the pivot column. So, how do we perform that? The pivot column is minus 2, 1 and 0, and the right hand side is 10, 1 and 1. Please note that the minimum ratios have to be performed only for the entries in the pivot column which are greater than 0. The negative ones have to be ignored. So, here only one positive entry is available in the pivot column. Therefore, we have only one minimum ratio, that is 1 upon 1. Rest of the two are not to be included in the minimum ratio test because they are either negative or they are 0. So, we have no choice and we find that the leaving variable is x6. So, x6 is the leaving variable and therefore, we will leave this x6 will leave this basis. Therefore, what do we find? We find that the entry marked in the pink cell, that is 1, this becomes the pivot and this is the pivot, and therefore, in the next iteration we need to convert this pivot column as 0 1 0. That is how we will make sure that x2 is in the basis. Now, you will observe that fortunately only the first entry, that is -2, has to be converted. So, we need to apply the elementary row operations in such a way that this column under x2 variable becomes 0 1 0. So, what are those elementary row operations? The elementary row operation is only one that has to be performed, and that is R1 should be replaced by R1 plus 2 R2, and once this is done, the resulting column will become 0 1 0, and that completes our second iteration. So, the third table looks like this. We have applied the elementary row operations on the first row, and therefore, again what is the BFS here? The BFS is x4 is equal to 12, x2 is equal to 1, x3 is equal to 1 and remaining zeros, all other variables zeros. So, again we repeat the process, we obtain the deviation rows as before, and before we do that we need to make the necessary changes in the C0 column, because now the basis has changed. The coefficient of x4 is 0, the coefficient of x2 is -1, coefficient of x3 is also -1. Now, you will observe now both the artificial variables x6 and x7 have been removed from the basis, and that is what we wanted. You remember, we do not want any artificial variable in the basis, and that is what we have got over here in this table. So, as before we will calculate the deviations. What are the deviations? 3 minus 0 minus 1 minus 1 multiplied by 3 0 minus 2, which comes to be 1. Second one is -1 minus 0 minus 1 minus 1 multiplied by 0 1 0, which comes out to be 0. Third one is -1 minus 0 minus 1 minus 1 multiplied by 0 0 1, which comes out to be 0. Next one is 0 minus 0 minus 1 minus 1 multiplied by 1 0 0, which again comes out to be 0. Next one is 0 minus 0 minus 1 minus 1 multiplied by -2 minus 1 0, which comes to be -1. Next one is -m minus 0 minus 1 minus 1 multiplied by 2 1 and 0, which comes out to be 1 minus m, and the last one is -m minus 0 minus 1 minus 1 multiplied by -5 minus 2 1, which comes out to be -1 minus m, and these entries we will record in the last row, that is the deviation row of table number 3. And what is the criteria for deciding the entering variable? The criteria is to determine the largest entry in this deviation row, and we find that the largest entry is the first one, 1, the rest of them are all negative. So, therefore, largest entry is in the first one, indicates that x 1 should enter into the basis, x 1 should enter into the basis, and the pivot column becomes 3 0 minus 2. And the next step is to determine which variable should leave the basis, and what do we find? We need to determine the minimum ratio between the right hand side and the pivot column. So, what are those? The pivot column is, the right hand side is 12 1 1, and the minimum ratios are obtained between the positive entries of the pivot column and the entries of the right hand side. So, therefore, minimum ratios are, there is only one, 12 and 1, because you find that here second entry should not be considered because it is 0, third entry should not be considered because it is minus 2. We need to look at only the first one. So, the first one is 12 by 3. So, therefore, the first variable x 4 should be the living variable, x 4 should be the living variable. And now we need to apply the elementary row operations in such a way that this column becomes 1 0 and 0. So, what are the elementary row operations that we perform? Yes, we perform these elementary row operations. R 1 has to be replaced by 1 by 3 R 1. Similarly, R 3 has to be replaced by R 3 plus 2 R 1, and this will make our pivot column 1 0 and 0. As a result, we will get the table number 4, and in the table number 4 you find that when you calculate the BFS obtained is x 4 is equal to 4, x 2 is equal to 1, x 3 is equal to 9, and remaining all as 0. So, we will look at how we can calculate the deviation rows, and the deviation rows are calculated as before. I have just recorded them here in the last row. Please check these entries, and you will find that all the entries in the deviation row are either 0 or negative. This indicates that the simplex procedure is supposed to stop, and the solution is the current BFS. So, the current BFS is the solution, and the current BFS is nothing but x 4 is equal to 4, x 2 is equal to 1, x 3 is equal to 9, and remaining 0, and that is the solution to the problem. So, therefore, what did we find? We find that in the big M method we take care of those inequalities which are of the greater than or equal to type, because in the greater than equal to type constraints we have to subtract a surplus variable, and because we are subtracting a surplus variable, we do not have a basic variable in that equation. Therefore, we need to add an artificial variable, and because we are adding an artificial variable, we need to make some adjustments in the objective function in such a way that at some later iteration those artificial variables will disappear from the basis. Ultimately, we find that is what happens. Here, as you see in this example also, the two artificial variables x 6 and x 7 are 0, they are no longer in the basis and they are 0. So, therefore, our objective is satisfied, and that is how the greater than equal to constraint is taken care of. Now, I hope everybody has understood the basic principle behind the big M method. As an exercise, I want you to solve this question. It is again you have two constraints, one constraint is of the less than equal to type and the second constraint is of the greater than equal to type. So, in the first constraint you will add a slack variable, in the second constraint you will subtract a surplus variable and you will get a basic variable in the first equation, but you will not get a basic variable in the second equation, and for that reason you will need to introduce a artificial variable in the second equation. Accordingly, you will have to make adjustments in the objective function. So, please write down this question: minimize x1 plus 2x2 plus x3 subject to 2x1 plus x2 plus x3 less than or equal to 2, and the second constraint is 3x1 plus 4x2 plus 2x3 greater than or equal to 16 and all x1, x2, x3 greater than or equal to 0. I hope everybody will be able to do this question. It is very simple and it is based on what we have discussed today. Now, after you have done this exercise, I want you to give a thought to what happens if in the simplex calculations, how can you recognize the following conditions, that is the LPP has a unique solution, the LPP has a multiple solution, the LPP has a infeasible solution and the LPP has a unbounded solution. Remember, all these cases we had discussed when we were studying the graphical method, but the graphical method is only for a two variable problem. However, in the simplex method and the big M method, we can solve an LPP in any number of variables. So, how to identify in the simplex calculation all these four situations needs to be known. So, please try to think about how you can find out the conditions in the simplex method for looking at these four conditions. Thank you.